Okay, so we're still asking the question, does series converge or diverge? And yesterday we got our first sort of solution in that direction. We got the we got two tests. The nth term test can't tell you if a series converges, though. It can only sometimes give divergence. The integral test in theory can tell you whether a series converges or diverges. The integral test is limited, though. It has some, all of these terms have to be positive, and it has this monotonicity condition. But really, the great weakness of the integral test is that you need to be able to take an integral. And frequently we cannot do that. Either we have rules that will let us do it, or we have something like a factorial, which it's impossible to integrate because it's only defined on the natural numbers. The comparison test in theory has a lot of advantages over the integral test. It retains this positivity condition. We can't deal with negative terms in the sequence, or the series, I ought to say. Otherwise, we don't have that monotonicity condition. We don't need to be able to integrate anything. The comparison test is, I can put some sort of pros and cons on the board, but let me first say what the comparison test is. And I think the great pro of the comparison test is that it makes a lot of sense intuitively. The comparison test says, well, suppose we have these terms A sub n, and these terms are positive, or at least not negative. 0 is less than or equal to A sub n, is less than or equal to B sub n. And suppose that the B sub n series converges, then the A sub n series converges. This is half of the comparison test. But before I go further, I mean, let's just try to understand it. It doesn't always quite work, but the intuition we should have is that convergent series are finite and divergent series are infinite. So if B sub n converges, then B sub n is finite. And it wouldn't make any sense to have an infinite thing that is less than a finite thing. So if we know that this B sub n is finite, then A sub n also has to be finite. You can't have an infinite expression that's less than a finite expression. And this is, this is why we need the terms to be positive, because if you allow your things to be negative, you know, the sum of -1. Well, this is -1 plus -1 plus -1 is clearly diverges, or I hope it's clear. It goes to -infinity, but this is less than, for example, the p-series. 1/2 to the n is the p-series. It's the geometric series. It's 1/2 to the n. It converges, so we're less than a convergent thing, but because we're negative, we still don't converge. So we do need these terms to be positive. The other half of this test you've got this series you're looking at. You're looking at a sub n. And now maybe these terms a sub n are bigger than something, are bigger than b sub n. The thing they're bigger than diverges. Well, again, thinking of convergent and divergent as finite and infinite. If we're bigger than an infinite thing, we are also infinite. So that's the comparison test. So sort of bullet point A and bullet point B, one for convergence, one for divergence, but it just gets called the comparison test. And the comparison test has things going for it. I do think the cons are going to outweigh the pros a lot of the time. But I think the great pro is that it's intuitive. I mean, if if I imagine trying to like explain the integral test to my dad, I mean, he's a very intelligent man, but no background in mathematics. I'd say, well, we're drawing these rectangles, and you see we're drawing these rectangles to be bigger than this region, and this not easy. Whereas the comparison test, well, we've got these things and they're big, they sum up to infinity, so these even bigger things also sum up to infinity. We've got these things, they're small, they sum up to a finite number, so these even smaller things sum up to a finite number. The main con of the comparison test, sort of the con that all of the other cons are going to spring from, is it requires you to figure out, or let's say to find, a second series. I mean, if I say, here's 5/2 to the n minus the cosine squared of n or whatever, and I say, approach this with the comparison test. Well, the series either converges or it diverges. If it converges, we need to find some other series B sub n such that B sub n also converges. Right? I mean, that's how the comparison test works. If we want to show this, then we need to find a bigger thing that is finite. I accidentally put the subscripts in the power there. We need to find a larger expression such that the larger expression is finite. And if we do that, then we can use the comparison test. And if maybe we think it diverges, maybe this is what we're going to try to show. Then we need to find these expressions B sub n that are less than it. Sorry, that are, yes, that's right, that are less than it, such that this smaller series diverges. Again, when I say if diverges, what I mean is that we suspect it diverges, and we are trying to show it, and this is how we would show it using the comparison test. And in both these cases, I mean, I say we need to find this other series, and the question that raises is an obvious one, I think. How do we find the other series? Another con of this test is that, I mean, unless you're just going to take a problem and flail at it for an unknown period of time, we need to be going into the problem with some kind of intuition. Do we think the series converges or do we think the series diverges? Because what we're going to do varies depending on the answer to this question. I mean, it's related to the second series. We need to find a second series, and that has to be either bigger or smaller than the series we're looking at. And whether it needs to be bigger or smaller depends on whether we're going to show convergence or divergence. So unless we really are just flailing around in the dark, we need this intuition, and I mean, I'll go ahead and I feel like I'm coming down very hard on this test, but a sort of sub-con of this is that when we have that intuition, there's a different test that lets us use that intuition correctly, and that's often much easier to use, the so-called limit comparison test. And I'll talk about that tomorrow or Thursday, but the reason I say this different test is often easier is that it's mechanical. It needs less messing around trying to find a second series. Well, we'll see when we get to it. So yeah, the comparison test, not easy to use, is my judgment on it. And I don't want to obsess about this test also, just because when we get to applications, we'll see. I mean, the comparison test is not the test we normally want for applications. You can whack that on as an additional con if you want. Still, it's part of the curriculum. It's part of every calculus class's curriculum. And if you end up teaching this, I don't know how likely that is unless you go into college teaching. I think normally high school calculus curriculums end at about the same place our calculus 1 class does. But if you do end up teaching it, you need to be familiar with it. And to talk about this, so in general, these series we're looking at are all fractions. I mean, you've probably observed that. And when we talk about, we need a bigger series or we need a smaller series, the way we approach that isn't just to guess series and fumble around and totally in the dark. It's to look at the numerator and to look at the denominator and to ask, are there obvious ways that I can make this series bigger or that I can make this series smaller? So to increase a fraction, we can increase the numerator, or we can decrease the denominator. So, 1/2 is less than 5/2. 1/2 is less than, since we're keeping these fractions positive, we'll say that. You see, when the numerator goes up, the fraction gets big. When the denominator goes down, the fraction gets big. To decrease a fraction, well, it's the opposite. To make a fraction small, we can decrease the numerator. or increase the denominator. We have 5/7, and we want to make it smaller. Well, 5/7 is bigger than 1/7. Or if we want to make it smaller, 5/7 is bigger than 5/10. And we look, let's dive into an example now. 5 over 5n plus 7. And we'll see if we can show that this either converges or diverges using the comparison test. And as I say, unless we're just going to, let's try making it small. Oh, that doesn't work. Let's try making it large. That didn't work either. Okay, let's go back to small. I mean, unless we want to do a lot of that, we need to have some kind of intuition about whether this converges or diverges. And this looks a lot like a series we've already studied, whose convergence or divergence we already know. Which series is that?
Is it the P series?
So I wouldn't say it looks a lot like the P series, because the P series have powers in them, and I'm not seeing powers here. What I do think, remember that n is going to infinity. So I mean, when n is a billion, and we have, a +7 or a -2 or whatever, these fiddly little things, when n is getting big, 5 over 5 billion versus 5 over 5 billion and 7. The 7 basically might as well not be there. And 5 over 5n, those 5's cancel. That's 1 over n. That's the harmonic series. The harmonic series diverges. So we look at this and we say, this looks a lot like a divergent series. So it probably diverges. That is going to be our guess. And if we're going to show divergence, then what we need is to shrink this. That's, again, the way the comparison test works. We either shrink it or expand it, increase it, depending on whether we're trying to show convergence or divergence. Here, the only way we can show divergence is if we're bigger than an infinite thing. It's useless to go the other way. This is certainly smaller than, well, in fact, it's smaller than 5n plus 7. It's smaller than 1. And the sum of a bunch of 1s is infinity, but being smaller than infinity is not useful. It doesn't tell us anything. we need to be bigger than infinity. Yeah. And we say, okay, so we're trying to decrease the fraction. And again, we're trying to decrease the fraction in a kind of artistic way. I mean, this is certainly bigger than 0, but that's useless because 0, this is convergent, and being bigger than a finite thing doesn't tell us anything. So we're trying to do it in this very specific way so that we find a smaller but infinite series. And then use the messing around phase of this problem. Because it's our first problem, I've picked one that doesn't require a huge amount of messing around. If we're trying to decrease this fraction, we have some options. The first option is to decrease the numerator, but that's not hopeful to me. And the reason I say it's not hopeful is that a constant multiple of a convergent series converges, and a constant multiple of a divergent series diverges. And the takeaway of that is this 5 up here. I mean, I could rewrite this to make it explicit. This is a constant multiple of a series, and whether, if we replace this with 4, it's still a constant multiple of this series. If we replace it with 1/1,000,000th, it's still a constant multiple of this series. So this is just converging or diverging with this. And since the details of the 5 aren't really doing anything, I mean, we could replace the 5 with a 1 if we wanted to, for example. And now we look at this and we say, well, we don't know whether this converges or diverges, so we have to keep going. Actually, now that I look at it, the thought does occur to me that this would be an excellent application of the integral test, but we'll go on using the test we started with. We'll go on using the comparison test. So making 5 smaller doesn't really seem to be useful. What if we make the denominator bigger? Yeah, I copied this incorrectly and it's gonna be let's do this as our second example, but for our first example, let's correct that. Let's put subtraction there, just to make our first example as straightforward as possible. So can we make 5n minus 7 bigger? Well, I mean, that's sort of a weird question to ask, because I mean, sure, it's less than a lot of things. It's less than an exponential function. It's less than a quadratic. But we can make this bigger in a relatively simple way. Which is that at the moment, we have subtraction dragging it down. We've got that -7 term. If we got rid of the subtraction, that would make the denominator bigger and it would make the entire fraction smaller. 5/5n is 1/n, and we have accomplished our brief. 1/n is the harmonic series. It's infinite. It diverges. So we have found a smaller but infinite series. And the comparison test says, well, if we're bigger than something infinite, we are also infinite. And this series does diverge. The comparison test can be quite fiddly. I started to feel sort of bad for it, so I stopped with the cons, but pretty minor changes to the sequence, or I should say series that we're looking at. Changes that really shouldn't affect convergence or divergence can significantly affect how the comparison test is applied. That's why I changed this problem midway through. Let's now look at the original problem. Let's look at this. And again, trying to use our intuition here. We don't care what happens when n's small. N's going to infinity. N's, a million or a billion or a trillion. And again, this 7 really shouldn't be doing much of anything. 5 trillion plus 7 versus 5 trillion. It's basically the same number. So we have the same kind of intuition that if we ignore this 7, this is the harmonic series diverges, so this looks a lot like the harmonic series. It looks a lot like a divergent series. And our intuition hasn't changed. We thought that 5n minus 7 diverged. We think that 5n plus 7 diverges. I think that 5n minus 12 or 5n plus 17 diverge for the same sort of reason. It looks like a harmonic series. So changing that subtraction to that addition doesn't change our intuition, but it does change how we have to approach the problem. It changes the details of, okay, we're going to take this and we're going to mess around with it, and eventually we're hopefully going to wind up with a smaller but infinite expression. Again, decreasing 5 doesn't seem super, what am I? Yes. Decreasing the 5 to a 2 or a 1 or a whatever doesn't seem super hopeful to me. What about increasing the denominator? Well, again, I mean, when we talk about increasing the denominator, it's easy to do. I mean, 5n plus 7 is linear. It will be less than a quadratic. It will be less than a cubic. But the hope is that we're increasing this denominator without messing around too much with it. And I mean, I'll tell you the reason we can't use a quadratic or a cubic, even though it would decrease this fraction, it would decrease the fraction too much. Instead of being bigger than an infinite thing, we would be bigger than a finite thing, and that wouldn't tell us anything. So we need to increase this denominator, but not too much. And it's, you know, the difference between this and the last problem. The last problem, we had subtraction. We just got rid of it to decrease the denominator. Here we got rid of this -7. We can't get rid of this +7. If we get rid of this +7, we're going in the wrong direction. So what can we do? And here's where we have to use our creativity, and problems can get difficult. I've mentioned, though, that n is getting big. You know, I've also mentioned that when we're looking at divergence or convergence, it really doesn't matter where we start. Like, we sort of assume we're starting at 1 a lot of the time if we don't have anything written there, but we could be starting at 1 or at 10 or 100 or 1,000, and it's not affecting convergence. So if we assume that we're starting at 1,000, say, we can assume that n is bigger than 7. And if n is bigger than 7, then 5n plus n is bigger than 5n plus 7. And if we replace 5n plus 7 with 5n plus n, now we are going in the right direction. We increased the denominator, so we shrunk the fraction. And we wind up where we need to be. That 1 over we no longer have 5's nicely cants thing, but that doesn't matter. We've got a constant times 1 over n. We've got a constant times the harmonic series, and the harmonic series is infinite. The harmonic series diverges, and 5/6 of infinity is still infinity. So So this diverges, but we had to totally change our argument. And we'll continue this tomorrow. That's fine. I had planned to give over more than one day to this. We'll look at some more complicated examples, like ones where we have to mess around with the numerator and with the denominator at the same time, that sort of thing. And I will see you then.